Throughout this presentation, I will be referring to this PLM-ALM change flow. The process starts with a new problem report created in PLM. Once created, the report can be accessed by any authorized PLM user. Problem report describes the issue in a free text and provides additional information such as dates and severity levels. In our case, the report was triggered by a change issued by FAA that affects an existing de-icing system for airplanes. Next, change request is created. The purpose of ECR is to manage process of investigating what changes are needed and their impact on the product. Typically, product manager starts a new ECR in response to a problem report. ECR content defines what needs to be investigated, suggests a possible solution, and provides additional relevant details. Problem report is one of the key elements of an ECR, and therefore it must be linked to it. This is a manual process, since it is a decision of the ECR owner how to characterize the issue. Next, affected items are added to the same ECR. ECR indicates what design artifacts need to be investigated. In this case, one of the items is the affected requirement itself, and other items are those affected by that specific requirement. The parts may be mechanical or electronic, or they may represent functionality implemented in software. They may also be entire assemblies. ECR groups them in one place so that the engineering teams will know what to start evaluating. Items are selected using typical PLM search and filtering tools for keywords, values, and properties. Again, the purpose of ECR is not to implement a change, but to investigate what changes may be needed and what impact that may have. These investigations involve various engineering teams, and they must be carried out with tools and processes specific to these engineering domains. And those processes are often different than processes specific to PLM. Often some items tracked by PLM have content that is managed outside of PLM. Here is an example of a PLM requirement managed indoors that uses OSLC link to reference its content. By clicking on the OSLC link, user can see that external content or can automatically switch to the external ALM environment. In this case, that ALM environment happens to be IBM Continuous Engineering Suite of tools. You can see this OSLC link in PLM led directly to the content of the requirement exposed in ALM. Once in ALM, user can explore all related data to ensure that the right context of the requirement is being referenced. You can also see that the requirement in ALM is the one referenced from PLM. The key point here is that while OSLC links the data, it's the PLM ECR process that provides the appropriate context for using these links. Next, ECR triggers corresponding activity in ALM. PLM ECR workflow manages how to involve engineering teams throughout the ECR process. Engineers that design product structures managed explicitly by PLM are notified of their assignments via PLM. Subsequent reporting of the task completion is critical to promoting ECR workflow state. For items with OSLC links linked to externally managed content, PLM workflow automatically triggers child work items in ALM as children of the task created in PLM. These ALM tasks retain OSLC links to the PLM ECR and vice versa, ensuring full traceability across ALM and PLM. OSLC links in ALM resources allow for dynamic display of the data residing outside of ALM. This is shown here by interacting from ALM with ECR in PLM and requirements indoors. Next, ALM is used to further investigate artifacts that are outside of PLM. OSLC links are the essential resource during this activity. Here is an example of accessing a PDF document associated with the project. Such documents are often related to, but not necessarily part of the requirements or other product specifications. An advisory circular, as the one shown here, may be something that is added to the environment at any point during system design and without PLM involvement. Similarly, ALM can use OSLC links to point to multiplicity of requirements in tools like doors that PLM may not be aware of. ALM environment provides many ways of organizing access to such information. Here, all ALM views help to expose additional relationships to requirements. Another example is a graphical representation of the relationships in ALM. These various representations help systems engineer to better understand context of the information. Here is an example of seeing OSLC linked data without exiting ALM environment. Next, ALM impact analysis is used to pinpoint scope of the proposed change. System-level product structure view is where such analysis is often initiated. ALM environments provide a multiplicity of system structure views, including interactive navigation of the relationships between them. The context of these ALM system views typically come from the related SysML modeling tools. Here is an example of a SysML definition exposed by IBM Rhapsody, including graphical navigation within ALM view outside of Rhapsody. In ALM, systems engineer is also able to execute system-level analysis with the context of physical product configurations managed by PLM. While system structure view is not easily captured in PLM, PLM-managed part models can be exposed to ALM via OSLC links. Here is an example of that. Here is another example of how ALM allows to see PLM-managed artifacts without leaving ALM environment. These various views in ALM show PLM-managed ECRs and ECOs and how they relate to each other. Again, same information is provided in various graphical representations. Systems engineer can view the content as an OSLC resource or use OSLC link to open the item in PLM. Once the impact analysis is completed in ALM, systems engineer documents the results in the associated ALM tasks. Since the tasks are linked to PLM ECR via OSLC links, same information becomes exposed in PLM as part of that ECR. Finally, systems engineer can expose and navigate state of the related PLM ECRs without exiting ALM. This diagram shows a view of such ECRs together with ALM tasks initiated by these PLM managed ECRs. And OSLC links again allow to expose the related PLM content interactively. Next, ALM results become part of PLM managed ECRs. Once impact analysis tasks are completed in ALM, systems engineer promotes all related tasks in ALM to a completed state, and the ECR process switches back to PLM. All engineers, systems, mechanical, electronic, software, follow PLM process to dispose of their corresponding tasks in PLM. ALM team members can use OSLC links in the respective ALM tasks to reach the appropriate ECR tasks in PLM. PLM ECR workflow automatically monitors individual completion rates. When the last vote is delivered, PLM workflow promotes ECR to the next lifecycle state in review. This cross-linking enables persistent traceability between ALM and PLM reporting of analysis results. This is critical since these results do impact subsequent implementation of changes. Next, project management team decides if ECO is warranted. If the ECO impact analysis does not fully justify implementation of the changes under consideration, the PLM ECR-ECO process has reached its end. Otherwise, a new ECO is initiated in PLM. The purpose of ECO is to manage implementation of changes. Product manager starts a new PLM ECO and populates impact matrix with PLM managed items that must be changed: assemblies, mechanical, electronic, software requirements, documentation, etc. And some of these items may have their content linked to ALM via OSLC links. Next, ECO authorizes engineering to implement changes. Not all parts in ECO affected assemblies will be changed, although all will be part of the new assembly. Part in PLM ECO with OSLC links to ALM automatically trigger child work items in ALM. This cross-linking maintains persistent traceability between ALM and PLM digital twins. PLM ECO workflow controls the rest of the release process of items affected by ECO. Implementation of changes is initiated simultaneously in all respective domains: ALM, mechanical, electronic, etc. This is a key point because PLM process is not the same as engineering design process within the respective domains. Next, implement changes in PLM. Work in ALM follows its own rules and workflows and is independent from work on mechanical and electronic parts controlled by PLM. At the same time, systems and software engineers can easily reference content of PLM ECO from the LAM environment using OSLC links. Again, this maintains persistent traceability between ALM and PLM digital twins, a digital thread. Next, ALM engineers update PLM ECO status. ECO remains unreleased until systems and software engineers complete their tasks in PLM. This may involve uploading to PLM of the latest software build to make it part of the physical product structure managed by PLM. PLM can manage software as a link to a build process, as a binary file, or as a software part number with a revision. Here, the process shows upload to PLM of the actual ALM-generated binary file as an artifact of a software part. PLM ECO workflow waits for all tasks to be reported by engineers as completed. ALM systems engineers update all related tasks in PLM as completed as well, in addition to doing that in ALM. Once all is done, PLM ECO process transitions affected assemblies and parts to the released state. Here you can see how final voting is performed, including completion of the related tasks, and the related structure is being released with a new rev number. The ECO is released and all of the affected parts are also marked with a subsequent rev The one with A is the only one that was not changed within the structure. Integration of PLM ALM change process results in persistent and traceable digital thread that links functional and physical digital twins.